Welcome back, everyone. The purpose of this video is to continue on in our discussion of solutions and colloids, and we are going to pick up with the topic of colligative properties. So, the properties of solutions differ considerably from those of the pure solvent and the pure solute. And some solution properties are going to depend on the type of solute that you have. For example, you've got acidity or density. But colligative properties are special because they do not care on what type of solute that you have, not its nature, but instead on the number of solute particles that you have, so on the concentration. And some examples of this are vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. And so we're going to spend the majority of this video talking about each one of these colligative properties in detail. But before we get into that, we've got to stop and talk about the concentration units that we're going to use in these equations. So in General Chemistry 1, you were introduced to molarity, and you may need to go back and review how to calculate molarity if you're given the mass of the solute and the volume of the solution, or how to determine how you would form a specific concentration of a solution. So how much solute would you need, or how much solution, what volume would you need in order to form a solution with a specific concentration, right? So basically using molarity as a conversion factor. So anyways, go back and review molarity, but the issue with molarity is that it is temperature dependent. And so most of these colligative properties, they are going to vary in temperature, whether we're looking at boiling points changing or freezing points changing. And so because that temperature is not constant, we're going to have to use some different type of concentration units. And so we're going to see the use of mole fractions and molality. So mole fraction is simply going to be the moles of a substance of interest divided by the total moles of all of the solution, right? So all of the mole fractions in a solution should add up to a value of 1, which means that if you know the mole fraction of the solute, and let's say you only have one solute in that solution, then you could simply subtract the mole fraction of that solute from 1 and get the mole fraction of the solvent, right? So this is actually pretty important, and you'll end up using that fact that the mole fractions need to add up to 1. Now, molality is going to be the moles of the solute divided by kilograms of solvent. And again, it's very important to note that it is divided by the mass of the solvent, which is different than molarity, which is the volume of solution, right? So that's going to be important if you're trying to convert between molarity and molality because of that difference between solution and solvent. So let's go through some practice examples with the unit concentrations. We are going to start by determining what is the molality of phosphoric acid in a solution of 14.5 grams of phosphoric acid in 125 grams of water. So remember that in general, molality, right, is going to be the moles of the solute, and so when they say the molality of phosphoric acid, that tells you that that is your solute. So it's the moles of H3PO4. Right, you can also tell this because the amount of phosphoric acid, that 14.5 grams, is less than the 125 grams of water. So the smaller amount is going to be your solute, and the, the smaller amount is going to be your, let's see if I can write down here. Solute, there we go. And the greater amount will be your solvent. Okay, sorry about that. So we've got the molality is moles of our solute phosphoric acid out of kilograms of our solvent, which must be water. All right, so we first need to determine the moles of phosphoric acid from the grams, and so we know how to do this by now, right? We're going to need that molar mass. So we take the 14.5 grams and we are going to divide by the molar mass of phosphoric acid, which is about 97.995, probably keeping more digits here than I needed to, and per 1 mole going on the top there, so grams cancel. We're going to keep 4 sig figs throughout because we started out with 3 sig figs to prevent round off errors, so we're going to get 0.1480 moles of our solute. Now, they give us the grams of our solvent, but of course we need it in kilograms, and so remember there's 1,000 grams in 1 kilogram, so we've got 125 grams, and then there's 1,000, so we need to divide by 1,000 per 1 kilogram. Okay, so basically we're going to move that decimal over 3 places to the left and get 0.125 kilograms of our solvent. So now we have the moles and the kilograms. We can simply divide those out, and so molality is going to be 0.1480 moles per 0.125 kilograms, and we need to round to 3 sig figs, and so that gives us 1.18 molal concentration, and so we use a lowercase m to represent the units for that. Okay, second example. Now this one is a unit conversion where we're trying to convert from molality to molarity. And so if they give you the molality and the density, you can calculate the molarity. So the way we do this, we do have to kind of strategize and assume that we have 1 kilogram of the solvent. And the solvent in this case, of course, like last time, is going to be water. And we know that because it's an aqueous solution, so 1 kilogram of H2O. If we assume 1 kilogram of H2O, of course, that contains 33.7 moles of our solute nitric acid. Okay, now given that information, and of course I know that it's 33.7 moles per 1 kilogram because of molality, right? 33.7 molal concentration tells you that it's 33.7 moles of solute per 1 kilogram of solvent. So given that information, I'm going to determine the mass of my nitric acid in 1 kilogram of solvent. Okay, so if I start out with that 1 kilogram of water, and use my molal concentration, of course I'll get that 1 kilogram to cancel out, and you don't necessarily have to do this step. You could just start out with the 33.7 moles of your solute. And that is out of 1 kilogram of H2O, right? So all I'm doing is I'm taking that molal concentration and writing it out with units so that the kilograms of water cancel out. And then to convert from moles to grams of nitric acid, I'm going to use that molar mass. So the molar mass of nitric acid is roughly 63.01. And this is grams per 1 mole. So moles cancel, and I'm left with the grams. Of course, I'm going to keep 4 sig figs until I'm done, and so that gives me 2,123. I'm subscripting that 3 because it's not significant, but of course it's important for magnitude, so we do have to keep it, and that is grams of HNO3. Okay, so if we want to determine the entire mass of the solution, we have to add the mass of the solute plus the mass of the solvent. And so by assuming that we had 1 kilogram of water to start out with, right, 1 kilogram is 1,000 grams. And so the total mass of my solution and I'll abbreviate that as SOLN, that has got to be equal to 1,000 grams of my solvent, which is water, again because I assumed 1 kilogram from the start, plus the mass of nitric acid that I just calculated, that's the 2,123 grams. And so this should give us a total of course, 3,123 grams, and now that is the mass of my solution. So this is important because whenever we look at density values, density is always out of the solution, right? So those grams and milliliters are both describing grams of solution out of milliliters of solution. So I can't use the density unless I have either the mass or the volume of solution. Okay, so now I've calculated the mass of the solution. I can use that density as a conversion factor to determine the volume of the solution. And remember, molarity, right? Molarity is equal to the moles of my solute over the liters of solution. And so if I use that mass and density to determine the volume of solution, then I'll have my volume of solution, and I know how many moles of solute that I have, right? Because in 1 kilogram of water, this is my moles of solute, 33.7 moles. Okay, so that's kind of the whole purpose here, right? We know the moles of the solute. We're trying to determine the liters of solution if we have that specific amount of solute. And we simplified things by assuming 1 kilogram of water by the definition of molality. Okay, so we're going to take that 3,123 grams of solution, using the density as it is, let's see, 1.35, we're going to need to flip it, right? 1.35 grams per 1 milliliter. We're flipping it so that the grams will cancel, and that gives us milliliters of solution, but of course we want liters, right? So we're going to have to divide by 1,000 milliliters in 1 liter. And so keeping at least 4 digits there, we get 2.313 liters of solution. Okay, so now I know the moles of my solute. I've found the liters of solution for that amount of solute. And so I can simply divide those two numbers out, right? We need this number as well as the 33.7, and then we can determine the molarity. So 33.7 moles of nitric acid out of 2.313 liters of solution. And we want to round this to 3 significant figures, and that leaves us with 14.6 capital M for molarity. Now, just note that whenever I'm trying to solve for this, notice how I'm constantly saying kilograms of what, right? It's kilograms of water, it's moles of nitric acid. I've constantly got to keep in mind whether I am looking at the solute, the solvent, or the solution, the total of the two, right? And if I don't keep up with that, it's going to be really difficult to keep up with the problem. So make sure you write down next to each unit whether you're dealing with the solute, the solvent, or the solution. Okay, so the first colligative property that we're going to look at is vapor pressure lowering. So when we add a non-volatile substance to a volatile liquid, it is going to result in lowering that liquid's vapor pressure, right? And the reason that this happens, probably the simplest way to think about it, is that the presence of that solute is going to decrease the surface area. And so when you decrease the surface area, you're reducing the rate of solvent vaporization. And so if we reduce the rate at which the solvent vaporizes, we're going to end up with less solvent particles in the air, and so that's going to, of course, reduce the vapor pressure. Okay, so this applies with Raoult's law. Raoult's law talks about the relation between the vapor pressure of a solution and the mole fraction and the vapor pressure of the pure solute and solvent. And so PA represents the vapor pressure of a substance of interest, but it is specifically the vapor pressure of that substance of interest in the solution. Okay, and that is going to be equal to XA. Remember, X represents our mole fraction, and then the second vapor pressure is going to be based on the pure substance. And so this could be, right, the pure solute or the pure solvent, depending on if both substances are volatile. Now, non-volatile substances, their vapor pressure is going to be negligible, so we'll assume it to be 0. And if we do that, then the vapor pressure of the solution is going to depend only on the vapor pressure of the solvent, right? Okay, so we're going to see this in our example. In the example, a solution contains 5 grams of urea, and that's going to be a non-volatile solute. So the only substance that's going to contribute to the vapor pressure will be the solvent, which in this case is water. Okay, so we have 0.1 kilograms of water. If the vapor pressure of pure water is 23.7 torr, what is the vapor pressure of the solution, assuming ideal behavior? Okay, so we are going to need Raoult's law, where the vapor pressure of that substance in solution is going to be equal to the mole fraction of that substance times the vapor pressure of that pure substance. Now, because we only care about the solvent, and again, that's because our solute is non-volatile, then essentially we are looking at the vapor pressure of water. Okay, so I'm going to swap out those A's to represent water in all 3 cases. So when they're asking what is the vapor pressure of the solution, they are essentially asking what is the vapor pressure of the water. So to do this, we're going to need to calculate the mole fraction of water. And remember, the mole fraction is going to be the moles of your substance of interest divided by the total moles of the solution. And so we're going to have to calculate the moles of the solute as well as the moles of the solvent. We've got 5 grams of urea, so that's our CONH2, and we need the molar mass of that. We're going to divide by the molar mass, which is roughly 60.06. Remember, I'm getting these from the periodic table by adding up all of the elements in the compound. So those grams cancel, and we're left with moles of our solute, which is 0.0832. Again, starting with 3 sig figs, so I'll carry 4 for now, and that is moles of urea. Okay, we're going to do the same thing with the water, but of course the issue is that instead of grams, they are giving us kilograms, so 0.1 kilograms, and we will first need to convert that to grams by multiplying by 1,000. So write 1,000 grams per 1 kilogram to get those kilograms to cancel, and then we can divide by that molar mass of water, which is roughly 18.02 grams per 1 mole. Okay, so grams cancel. That leaves us with moles of water, and keeping 4 sig figs, we will get 5.549 moles of our solvent, or moles of water. Okay, so if you want to calculate the mole fraction, then we will take the moles of the water, that's the 5.549, and then divide that by the total moles of everything, and so we have to add that water back with our solute 0.0832. Okay, and so you get back a mole fraction of water. Of course, you should anticipate that it will be getting close to a value of 1, right? Because water is going to make up the largest amount of that solution. And so you get 0.9852 for your mole fraction of water. And so remember, to calculate the vapor pressure of the solution, we simply take that mole fraction of water and multiply it by the vapor pressure of pure water, which they tell us is 23.7 torr. And so we're going to take that mole fraction times 23.7 torr, and 3 sig figs in our final answer. That gives us 23.3 torr. Okay, so again, just make sure that you're converting all of those masses into moles, and that those masses are in grams before you use the molar mass. Okay, one more example with Raoult's law. In that first example, we were looking at a non-volatile solute, but that's not always the case. In this solution, we have got 2 volatile substances. Methanol has a vapor pressure of 94 torr in its pure substance, and then pure ethanol has a vapor pressure of 44 torr. So neither of these are negligible, and we're going to have to account for both. And so the first step, if we want to be able to determine the vapor pressure of solution, is that we need to find the mole fraction of each individually. Okay, and so we know this by now. We're going to take those masses and convert them into moles. So we've got 50 grams of methanol, CH3OH, and divide that by its molar mass, which is roughly 32.04 grams per mole, right? And we get 1.561. Okay, and then we'll do the same thing again for the ethanol. So dividing by its molar mass of 46.07 grams per 1 mole. And we get 1.085 moles. And so we'll just kind of abbreviate these as M for methanol and E for ethanol. And so if I want to calculate the mole fraction of methanol, Of course, that's going to be the moles of methanol divided by the total moles of everything. Okay, and I am going to keep an extra digit here. If this was your final answer and these were the only two things you were looking for, you would round off to 3 significant figures. But because we're going to use these values in the next part, then I'm going to keep it as 0.5899. Mole fractions do not have units because it would be moles divided by moles. And then we do the mole fraction of ethanol, that's 1.085 divided by that same total amount of moles that we had from the first calculation, right? So that's coming from here. And that will give us 0.4101 for the mole fraction. Okay, so in the next question, it is asking us to calculate the vapor pressure of methanol and of ethanol above the solution. Okay, and I also would like to look at what the vapor pressure of the total solution is. So if we want to look at the vapor pressure of the total solution, then we're going to need to add together the two vapor pressures of each individually. Okay, so that's going to be the mole fraction of the methanol times the pure partial pressure, or sorry, the pure vapor pressure of methanol, and then add that to the mole fraction of ethanol times the pure vapor pressure of ethanol. Okay, so if we add these two together, you've got the 0.5899. That was the mole fraction of methanol from the previous example, and then they tell us that the pure vapor pressure of methanol is 94 torr. Okay, and then we're going to do the same thing for ethanol, pull that mole fraction back from the previous example. And of course, you know, if you wanted to double check those two mole fractions that we have, the 0.5899 and the 0.41, that should add up to very close to a value of 1. And then we're going to multiply by the pure vapor pressure of ethanol, which is 44 torr. Okay, so remember when you are accounting for sig figs in a combination of multiplication and addition, you're going to want to take this one step at a time, because remember that the rules for significant figures, they are different for addition than they are for multiplication. So in this first step, when we multiply the numbers, we should get 2 sig figs. And so the vapor pressure of just methanol would be 55.5 torr, right? And rounded to 2 sig figs would just be 55 if we were done. Or I guess technically, sorry, 56. So 55.5 torr for the methanol, and then again for the ethanol, that needs to be 2 sig figs as well. And so we get 18.0 torr. Okay, so when we add those two values up together, remember that it is based not on the number of significant figures, but on that decimal place or on that place value. And so both of them have significance out to the ones place, which means our answer needs to be reported out to the ones place as well, which is conveniently 2 sig figs. And so if we round that to the ones place, we get 74 torr for our final answer. Now that is the pressure of the solution, right? So that's the vapor pressure of the entire solution. And then 18 would be the vapor pressure of just ethanol in the solution, and 55.5 would be the vapor pressure of just methanol in the solution. Okay, so we've wrapped up vapor pressure. The next colligative property that we'll talk about is the boiling point elevation. So remember that boiling point is going to be the temperature at which the liquid's vapor pressure is equal to the external pressure. And if we're talking about atmospheric pressure, that's typically a value of 1 atm, right? So if we are lowering the vapor pressure of a solution compared to the pure solvent, right? So we're decreasing that vapor pressure. That means that we're going to have to increase the temperature to reach the same boiling point as we had with that pure substance, okay? And for this reason, when the vapor pressure is decreased, we have an increase in that boiling point. And so we get what's called boiling point elevation. And that's represented as a change in temperature, a change in T, and then the lowercase b represents the boiling point. So this is going to be directly proportional to the molal concentration of the solute in the solution. And the K represents a boiling point elevation constant. And this is going to depend on the identity of the solvent, right? So it does not matter what the solute is. All we care about is the total number of solute particles, which is represented by the molality in the equation. And then the Kb, your boiling point elevation constant, that's going to depend on what solvent that you have. Okay, so let's do an example with boiling point elevation. And remember that that change in T, that change in temperature, that represents the change in your boiling point, right? So you'll have to add that back to the original boiling point of the solvent in order to get the new boiling point of the solution. So what is the boiling point of a solution of 1 gram of glycerin in 47.8 grams of water? And they do give you the Kb value. So if they don't give that to you in your homework, just know that you can look up boiling point and freezing point constants, those K values, in your textbook or online, okay? But they'll be provided to you on a test. So what is the boiling point of a solution? We're going to need the equation delta T is equal to the constant times our molal concentration. So of course we need to calculate the concentration, and that means taking the grams of our solute, and remember the smaller amount is our solute, right? And then water is our solvent. Okay, so we need to take the 1 gram and divide by that molar mass. So we're going to flip the molar mass, which is roughly 92.09 grams per 1 mole. Okay, and that gives us roughly 0.0109. We only need to keep 3 digits, only 2 digits of significance from the 1.0, and this is moles of our solute. Okay, and then we can take the grams of water, the grams of our solvent, convert that into kilograms. Okay, and so that's going to be 0.0478 kilograms. So remember that just means moving that decimal place over 3 places. And so to calculate the molality of the solution, we're going to take that moles of solute divided by the kilograms of water, the 0.0478. Okay, and that gets us a molal concentration of 0.227. Okay, and now we can plug that into the equation where we calculate the change in the boiling point is going to be equal to the constant of 0.512 and that is degrees Celsius per molal, and then times that 0.227 that we just calculated, the molal concentration of our solute. Okay, and keeping at least two digits of significance, that gives us 0.116 degrees Celsius. Okay, now remember, this is the change in the boiling point, so we need to account for the original boiling point of water, and of course the boiling point of H2O, of water, is 100 degrees Celsius. Okay, so we're going to have to add to that original boiling point the 0.12 roughly degrees Celsius, and remember this rounded is 0.12 for a new boiling point of 100.12 degrees Celsius. Of course, we're assuming that 100 degrees Celsius is an exact number, at least out to two digits, to two decimal places out, right? So that gives us 100.12 degrees Celsius for the new boiling point of the solution. Okay, so very similar to boiling point elevation, we've got freezing point depression. So just like the boiling point increases with a solution compared to the pure solvent, the freezing point is going to go down. Okay, so we have basically the same equation. The change in that freezing point is going to be equal to the freezing point depression constant times the molal concentration of the solute, and that constant is still going to depend on the identity of the solvent. Just keep in mind that your freezing point depression constants, those are different than your boiling point elevation constants. So just make sure that you're pulling the right K value from the table. Okay, now whether we're dealing with boiling point elevations, freezing point depressions, or osmotic pressure, which we'll see in a few minutes, any of those colligative properties we can use to determine the molar mass of the solute. And we can do this as long as we know the mass of the solute that was used and the mass of the solvent, right? So if we weigh the solute and the solvent before we make the solution, we can determine what the molar mass of that solute is. And that's because if we look at the change in temperature from either that boiling point elevation or that freezing point depression, so based on that change in temperature, and as long as we know the K value because we know the solvent, we can find the molality. And as long as we know the mass of the solvent, we can find the moles of solute in that solution. And if we know the mass of the solute and we know the moles of the solute, of course we can find the molar mass in grams per mole. Okay, so just know that this could apply to boiling point elevations or osmotic pressure. Any of those, we can calculate the molar mass of an unknown solute. So we have a sample of an organic compound. It's a non-electrolyte, and we'll see why that's important near the end of the video. But we have an organic compound that weighs 1.35 grams, and it lowers the freezing point by 3.66 degrees Celsius. Assuming ideal solution behavior, we're going to calculate the molar mass of that compound, and of course they give us the K value here. So going back to that equation, that the change in temperature of that freezing point equals the constant times the molality, right? This time they give us the change in temperature, the change in temperature of that freezing point is 3.66 degrees Celsius. So we know 3.66 degrees Celsius is going to be equal to the Kf value that they give us, 5.12 degrees Celsius per molality, and then times that molality value that we don't know. So of course, molality will be equal to 3.66, taking the change in temperature, divided by the K value, the equation constant of 5.12 degrees Celsius per molal. So the degrees Celsius cancel, and of course dividing by molal twice kicks it up to the top. And so we get the concentration is equal to 0.7148, and that is moles of our solute divided by 1 kilogram of our solvent, and they tell us that the solvent is benzene. Okay, so I'll abbreviate that. Now, we are given the amount of benzene that we have. There's 10 grams. So we can use molal as a conversion factor. Start out with that 10 grams of benzene. And of course, molal is in kilograms of benzene, so we're going to have to convert that 10 grams of benzene into kilograms by dividing by 1,000. So divide by 1,000 grams to get kilograms of benzene. Grams cancel. And now we can use that molal concentration, right, the 0.7148 moles of our solute. And this will get us moles of solute per 1 kilogram of your benzene. Okay, so that should give us 0.007148. Right, basically all we did was move that decimal place over 2 places because the 10 cancels out with one of the zeros in 1,000. And this is, of course, moles of our solute. Okay, so they give us the grams of our solute, right? And molar mass is grams per mole. So if we have grams and we have moles, we can calculate the molar mass by taking the 1.35 grams of solute divided by the moles of solute in that solution. And rounding our answer to 3 sig figs, we get 189 grams per mole of our solute. Okay, and so that can help us potentially identify an unknown solute. So the next colligative property that we're going to talk about is osmotic pressure. And hopefully from biology, this may be review that a semi-permeable membrane, right, only certain molecules or ions based on their size or polarity or something, only certain molecules and ions are going to be able to pass through a semi-permeable membrane. And one of the most iconic examples of this are our cell membranes, right? So osmosis is going to be the transfer of a solvent through this membrane. And so just keep in mind that a solvent is always going to flow into the side that has higher concentration, right? So the solvent flow is going to be in the direction towards whichever side has the higher concentration of the solute. Right, and that's to try to create equilibrium where we get the concentrations to be equivalent on both sides of that membrane. And osmotic pressure is when you reach that state of equilibrium between the hydrostatic pressure and the flow of your solvent. Basically, the solvent transfer rate is going to be equal to the osmosis rate, and so you don't have any bulk transfer of that solid or that solvent in either direction. Now, the osmotic pressure is going to be directly proportional, again, to the concentration. This time we're going to use molarity, as well as directly proportional to the temperature. And that R value is our universal gas constant. And because molarity is moles per liter, right, and osmotic pressure, we can solve for that in atmospheres, then we want the R value of 0.08206 because that has units of liters times atmosphere per mole Kelvin, right? So it has the units of liters that we need to cancel out with that molarity value. So again, anytime that you're using that gas constant, that means that temperature must be in Kelvin. Okay, so let's try an example using this equation. The osmotic pressure of human blood is 7.6 atmospheres at 37 degrees Celsius. What mass of glucose is required to make a 1 liter solution of aqueous, a 1 liter of aqueous solution for intravenous feeding if the solution must have the same osmotic pressure as the body at 75 degrees Celsius? Okay, so we're going to need that osmotic pressure equation, which is equal to the concentration in molarity times your gas constant R times your temperature in Kelvin. And so R, we know, has to be that 0.08206. Okay, and temperature has to be in Kelvin, so we're going to go ahead and take the time to convert our temperature of 37 degrees Celsius that's given to us. Add 273 to that. I'm not too worried about using 273.15 because the osmotic pressure only has 2 significant figures, and so 310 Kelvin is 3 sig figs, and that's enough. Okay, so we have our temperature in Kelvin, we have our gas constant. They give us the osmotic pressure of 7.6 atmospheres, and so we must be solving for our concentration in molarity. And by doing that, of course, if you know the molarity and you know the volume, right, 1 liter of solution, then you can determine the moles and therefore the mass of your solute, which is glucose. Okay, so plugging in all of our values for this equation, the osmotic pressure is 7.6 atmospheres, and that is equal to the molarity that we're going to calculate times our R value, okay, and times our temperature of 310. Okay, so just based on those units of R, right, over here, the kelvins will cancel, and the atmospheres will cancel as well, and so that will leave you with your concentration of moles per liter by the time that you flip it over. So molarity will be equal to 7.6 divided by the 0.08206 times 310. Okay, and again, you're going to flip those R units because you're dividing them, and so you'll get the liters on the bottom and moles on the top. Okay, and we'll keep 3 sig figs until the end, so that gives us 0.299 moles per liter, right? And to find the mass, we're going to use the volume that they give us, which is 1 liter. And again, this step may be more than you need to do, but we've got 1 liter of solution times the molarity. Okay, so of course that's just going to give you back that 0.299 moles of your solute. Okay, and then we can multiply by the molar mass to get the mass of our solute. And so the molar mass of glucose is going to be 180.2, and that is grams per mole. So moles cancel out, It leaves us with grams of the solute, and rounded to two significant figures because, again, that osmotic pressure was 7.6, and so we get 54 grams of glucose, C6H12O6. Okay, so some biological applications of osmotic pressure, right? And again, this might be review from your biology class, but just remember that an isotonic solution, that means iso, of course, same, right? So isotonic solutions are going to have the same concentration as that inside of the cell or across any semipermeable membrane. A hypotonic solution is going to be a solution that is lower in concentration than what is inside the cell. So remember that you're always going to flow, the solvent is going to flow to whichever place has the higher concentration of solute. So if a hypotonic has a lower concentration in the solution, right, and so this is just kind of a beaker and then your cell, of course, here, right, that cell is what has the higher concentration of your solute if you have a lower concentration in the solution around it. And so the solvent is going to flow into the cell, right? So all that solvent is going to pour into that cell, and the cell will eventually swell and maybe even rupture. And so you've got what we call hemolysis, which is the rupture of the cell. Okay, and then hypertonic, of course, that's going to be the opposite. That's when you have a higher concentration outside of the cell. So again, if we have another beaker, this time the solution outside is going to be higher concentration compared to what's in the cell. That's going to be lower. And so the solvent is going to flow outside of the cell into the beaker or the solution outside, and then you're going to shrivel and have what we call crenation, which is the shriveling of a cell. Okay, so in our images here, of course, on the end, we've got crenation. Right, on the right-hand side, on the left-hand side is hemolysis, so that's when you're going to have the swelling. And that occurs in a hypotonic solution. Hypertonic is going to be your crenation, and then in the middle we have an isotonic solution. So our last topic for our colligative properties deals with electrolytes. So up until this point, any solutes that we've been talking about have been non-electrolytes, right? Which means that they do not disassociate when they dissolve in water. But if we're talking about electrolytes, they will disassociate into multiple ions. And so what happens is that if you have, let's say, 1 mole of sodium chloride, just as an example down here, right, when that disassociates in water, it breaks apart into 1 mole of sodium ions plus 1 mole of your chloride ions. And so now you have 2 moles overall of your solute. Right, and remember our colligative properties, all they care about is the amount of solute that we have. So when electrolytes disassociate, you end up with more solutes than you would have if they did not. And one of the issues is that electrolytes, even strong electrolytes, are not going to completely disassociate into their ions. And so we have what's called a Van Hoff factor, represented as a lowercase I. And so Van Hoff factors, you can find tables in your textbook. We have one here where you would expect, as we showed with that sodium chloride, you would expect there to be 2 moles, right? You would have the sodium ion and the chloride ion. But because they do not disassociate completely, you end up with a Van Hoff factor based on a 0.05 molal solution, that I is slightly lower, right, of 0.19. So most of the time when we're doing problems like this, we're probably going to assume that the ions completely disassociate unless the question gives you the Van Hoff factor or tells you to use the Van Hoff factor from a table. So in this first example, we are asked to arrange the solutions in order of their decreasing freezing points. Now remember, freezing point depression is going to be equal to the Van Hoff factor, which we've been assuming was 1 up until this point, times the constant, your Kf, and times the concentration, the molal, of your solutes. So based on this equation, the larger your concentration is, the more that your freezing point is going to drop, basically. So if we want to organize these in order of decreasing freezing points, we basically want to organize them in a way that the molal concentration is increasing. So just keep in mind, if we have an increasing molal concentration, right, that's going to cause the change in temperature of that freezing point. It's going to increase the change, but it's freezing point depression. So the larger change that we have, the more we're going to depress that freezing point. And so an increasing molal concentration will cause a decrease in the freezing point of a solution. Okay, so organizing these in decreasing freezing points, we want to organize them in increasing molal concentration. Now, the issue is that these are electrolytes, and so we can't just assume, say, that 0.1 molal is only 0.1. We've got to look at the electrolyte and how it disassociates. And so you may have to go back and review your complete ionic equations. But if we've got 0.1 molal of Na3 PO4, okay, that's sodium phosphate, it's going to disassociate. Remember, the subscripted 3 from that sodium becomes your coefficient. And so we get 3 sodium ions, and we do not touch, right, the subscript of a polyatomic. So that stays as our phosphate ion with a 3 negative charge. Okay, so we have for every, and let's put this out for a second, for every 1 mole of our solute starting out, 1 mole of sodium phosphate, we have 3 moles of our sodium ion plus 1 mole from our phosphate ion. And so our Van Hoff factor, again, we're just going to assume that everything completely disassociates, is going to be 3 plus 1 coming from the sodium ions and the phosphate ions for a total of 4. Okay, so we have to multiply that Van Hoff factor times the molality. Okay, we assume that the Kf is going to stay the same and that all of these, the solvent is water, right? So because the solvent is consistent throughout, then all we're looking at is the Van Hoff factor and the molality. So we take that Van Hoff factor times the molality that we were given, the 0.1, and that gives us 0.4 molality for the first. Okay, so that is again for that sodium phosphate. Okay, now the next one, this is ethanol. And so remember, our alcohols and most of our molecular compounds, they're not going to disassociate unless they are strong acids or potentially strong bases. So this is what we call a non-electrolyte. And so if we start out with 0.1 molal of C2H5OH, right, it's just going to stay the same. It's still going to be 0.1 molal of the C2H5OH of your ethanol. So no change there. And then the next one, same way, right? We've got carbon dioxide. Again, that's all molecular, and so non-electrolyte. It's not going to dissociate into its ions because it's not ionic, and it's also not an acid or a base. So that will stay as 0.01 molal for your CO2. Okay, now the next one, of course, that is an electrolyte. We've got sodium chloride. We've seen this one before. So 1 mole of sodium chloride will dissociate into 1 mole of our sodium ion plus 1 mole of our chloride ion. And so the Van Hoff factor here ideally is going to be 1 plus 1 for each of our ions for a total of 2. And then we multiply that by the molality of that compound of 0.15. Right, and so we get 0.3 molality for sodium chloride. Okay, and last one, we've got calcium chloride, right? So 1 calcium chloride will dissociate into your calcium ion plus 2 of your chloride ions. Remember that subscript becomes my coefficient, and so I've got 2 chloride ions, and so my Van Hoff factor there will be 1 plus 2 for a total of 3, which I can then multiply by the molality of 0.2. Okay, to give me 0.6. And that's for our calcium chloride. Okay, so now I just basically organize them in terms of increasing molality based on the ions. So the smallest, I believe, should be our carbon dioxide. So I'm just going to list them based on the substance. Carbon dioxide will have the highest freezing point. And then next, I believe we have the ethanol. Okay, and then the rest of them, we should be looking at the 3 electrolytes. We've got the 0.4, 0.3, and 0.6. And so sodium chloride would come in next, followed by your sodium phosphate, and last, the calcium chloride. Okay, so just remember you have to disassociate into your ions, calculate what that I value is by adding up the coefficients for your ions and then multiplying by the molality. Okay, so last example. Assuming complete disassociation and ideal solution behavior, and what that means is that we are not going to use a Van Hoff factor from a table, we're just going to add up those ions. Calculate the freezing point of a solution of 0.724 grams of calcium chloride in 175 grams of water. Okay, so we already found that the I value for calcium chloride was equal to 3. We had 1 from the calcium ion plus 2 from the chloride ions. Okay, so we know that our I value is equal to 3, and the change in temperature of our freezing point will be equal to that I value times our freezing point constant times the molality of the solution before ionization. Okay, so of course we've got to calculate the molality of the solution by taking the grams, the 7 0.724 grams of our solute and converting that into moles. Okay, so dividing by the molar mass, which is 111 grams per 1 mole. Okay, so grams cancel. That leaves us with 0.00653 moles of the solute. And then we can divide that by the kilograms of solvent. Remember that just is taking the decimal over 3 places, and so it's 0.175 kilograms of water. And so we get a molality of 0.03727, keeping 3 sig figs. Okay, so we've got the molality. They give us the K value, and we now know what I is. So change in temperature of the freezing point will be our I value of 3 times the K value of 1.86 degrees Celsius per molal, and then times the value that we just calculated, the 0.03727. Okay, molalities cancel out. We're left with degrees Celsius, and out to 3 significant figures, that is 0.208 degrees Celsius. And of course, we do want to assume that that Van Hoff factor is infinite sig figs. We're not going to let that limit us. Now, because water is our solvent, we know that the freezing point of water, of course, is 0 degrees Celsius, and so we subtract that 0.208, and of course that's going to give us a negative 0.208 degrees Celsius. Again, assuming that that 0 degrees Celsius is infinite. Okay, so that wraps up our topic on colligative properties, and I'll see you next time.